In today's lab video, we will study network models and perturbations, and how I'll show you how one can use Mathematica or MATLAB to do some of these analyses. And following this, we finally can have our MATLAB Mathematica demo. So this shows you a histogram. This is the degree distribution, and this is the network itself for a Barabashi-Albert graph, and I can vary n and k, right, where n is the number of nodes that get added and k is the number of links that form. So if you see, if I decrease k, this looks very much like the Barabashi networks that we are generating with just no triangles, no clustering, right, and then if you slightly increase, you will start that clusters start forming. Wow, did you see the fundamental change? Completely different. And still the degree distribution remains perfect. You have a beautiful power law, no doubt about it. But the one hidden factor here is we've kept the original network the same, which is basically just this, like an edge. So because any kind of network could grow. So if you think back, the importance of the Barabashi-Albert algorithm is that it allows for network growth. So you did the growth using preferential attachment, whereas what Strogatz was network rewiring. This was network growth. So many real networks grow over a period of time. So if you have a city, it's not going to remain static. The social network in the city is going to grow over a period of time. And if you have a protein network, or if you have a power distribution network, all of these things dynamically change over time. Right? So in a protein network, you may have different operations. Maybe you'll have duplications and so on. Death too, but usually for the periods that are normally studied, death may not be very important in most of the but I mean it certainly can be modeled. But you see that the degree distribution remains nice, right? A clean power law. Maybe I should have a fit also showing you, so then you'll know how does gamma change as you vary n and k. Right? But you can see it becomes super dense. So this is one nice thing about Mathematica. It may be possible with other things as well. I can make the slider and show you how things vary as you vary certain parameters. It gives you a good picture of what's going on. Let's look at Watt-Strogatz. How does your Watt-Strogatz network look like? What is that? It's a big band, right? So there's only one point in the histogram, right? And I think I've set k as 2. So technically this code is not fully correct because these would be two different random graphs, right? I'm showing you one picture on the left and another distribution on the right. So in this case it's same because the p is 0, but when I change, I don't think the correspondence will be maintained, sort of. Not sure why this is not changing. Oh yeah, I need a different n. Yeah. So what happens? This looks very much like a random network, right? Not truly. It's, I don't know if you can fit up. Oh yeah, this looks like a Poisson to me, almost, right? But yeah, you need to really worry about the fit. But some intermediate stage, it looks very weird, very different. This is your regular lattice, but at some intermediate stage, you get very interesting behaviors. You may want to plot clustering coefficient and other things by the side, right? This is just to show you what can be done. Yeah, I think this was a built-in MATLAB thing. So So, when you have very low edges, so you can actually plot your characteristic path length or something, right? What happens when I keep increasing the edges, right? So, see how the distribution changes. This is sort of a cumulative distribution, so it's not that nice, but let me show you a different. This is an Shreni random graph, right? So, as you increase edges, you will see that at some point a giant component emerges. At some point you will have a single connected component, just watch, almost, yeah. You can see a nice binomial Poisson kind of distribution. So, you can just play around with these to understand some of the concepts. So, in this video we did look at network models, and in the next video we will take a closer look at how do we perturb and study perturbations using MATLAB, and I will also introduce you briefly to the concept of profiling, although from a MATLAB centric perspective, but it is a very interesting way to look at how fast your code runs, where are the bottlenecks and so on.